Hi, everyone. Today we're going to be talking about hypothesis testing. Hypothesis testing is a statistical method that allows us to make inferences about a population based on a subset or a sample of the data. It involves formulating two hypotheses. The first is the null hypothesis, H0, which represents the default or the no effect assumption. The second is the alternative hypothesis, that's H1, which represents the effect that we're hoping to find. We use data to assess the evidence against the null hypothesis in favor of the alternative hypothesis. That's what we're hoping to see. The outcome of this process is either to reject or fail null hypothesis based on a predefined level of significance, commonly denoted as alpha. This is, p-value of 0.05, which is typically what we use. The p-value is a probability measure that quantifies the evidence against the null hypothesis. It represents the probability of obtaining the result as extreme or more extreme than our current data, assuming the null hypothesis is true. A low p-value indicates a strong evidence against the null hypothesis, while a high p-value suggests weak evidence against the null hypothesis. It's sort of a bit of a word salad, isn't it? It's important to note that the p-value does not measure the probability of the null hypothesis being true or false. It only reflects the compatibility of our data with the null hypothesis. Now, when we're trying to interpret these p-values, it's essential to sort of prevent some common pitfalls or mistakes. A p-value does not imply the probability that the null hypothesis is true or the probability of making a mistake when rejecting the null hypothesis. Instead, it provides information about the likelihood of observing our data given the null hypothesis is true. Really, the key here is thinking about it from the perspective, what happens if the effect you were looking for didn't exist and the null hypothesis was true? How likely would you see this result strictly by chance? Now, the role of p-value in hypothesis testing, because this is a crucial meta concept for all of statistics. And it's crucial because it's guiding our decision-making in this type of hypothesis testing. If the p-value is less than our predefined significance level alpha, we reject the null hypothesis in favor of the alternative. Conversely, if the p-value is greater than or equal to alpha, we fail to reject the null hypothesis. Instead, the p-value should be interpreted as a continuous measure of evidence against the null hypothesis. The smaller the p-value, the stronger the evidence against the null hypothesis. However, it's important to consider other factors, such as the effect size and prior knowledge, when drawing conclusions from our data. P-values are super valuable in hypothesis testing. They're the foundation of much of our statistical thinking, certainly for the layman. And they're really helpful for helping us make informed decisions based on the compatibility of our data versus its ability to think about how likely this data would have occurred just by chance alone. If we really focus on understanding how they work, they can be quite useful. But again, as we'll learn later, machine learning has rejected the null hypothesis of p-values as the only solution, and we've gone in a different direction.